So in terms of doing a net ionic equation when you're working with strong acids, strong bases, weak acids, and weak bases, one of the things you need to be aware of is that a strong acid or a strong base will fully ionize. So just like our solubility rules for salts, our strong acids are also completely aqueous. The main strong acids you need to be aware of are HCl, HNO3, and then this next one is really for the most part, and this depends on what level of coursework you're in. H2SO4, the first hydrogen fully ionizes, the second hydrogen almost fully ionizes. So if you're doing just net ionic equations, you're not doing equilibrium or Ka expressions, you can go ahead and treat that sulfuric acid just like any other strong acid. The difference is it's going to ionize into two H pluses and an SO4. Now again, in theory, it's not completely 100%, but in terms of net ionic equations and stoichiometry and fully reacting, it'll go ahead and behave just as any other strong acid would. A few others you need to be aware of are HBr and HI with the halogens. HF is not a strong acid. If you think of fluorine's high electronegativity, HF is a weak acid, meaning that it doesn't fully ionize. It doesn't mean that it's safe. As a matter of fact, hydrofluoric acid is a very, very dangerous acid, but it doesn't fully ionize. And we'll talk about what to do in a net ionic equation with an acid that doesn't fully ionize. Again, a few others here just to note: HClO3, chloric acid, and HClO4 perchloric acid. And because those two are, that also encompasses HBrO3, HBrO4, and HiO3 and HiO4. So we've got bromic acid, perbromic acid, iodic acid, and periodic acid. And as far as memorizing strong acids, if you learn that list, that's probably enough. If you're in second level chemistry, you know that it's real easy to tell the difference. If you don't have a Ka value given or something about equilibrium, then you understand that it's strong, that it fully ionizes. We're just focusing right now on net ionic equations for those. In terms of bases, for the most part, any group 1A or 2A, so that's an alkali metal or alkaline earth metal that's with a hydroxide. The ones that you definitely need to know are sodium hydroxide and potassium hydroxide. Those are the two main ones that we're going to work with as far as strong bases are concerned. Again, what does it mean that it is a strong base? Strong base is something that fully ionizes, meaning it's not NaOH, it's Na plus and OH minus. Fully, completely ionizes, breaks apart. So by knowing that, that also lets us do net ionic equations when we're working with acids and bases. So the first one I'm going to start with is hydrochloric acid is added to sodium hydroxide. Again, from those words, you would write the formulas. You would take a look and you would predict the type of reaction first. Looks like a double displacement reaction. It is NaCl plus HOH. Again, doing this as HOH to make it a little easier to balance, H and OH, and it balances with all ones. Now ready to do the net ionic. Hydrochloric acid, strong acid, aqueous. Sodium hydroxide, strong base, aqueous. Now we've got a salt rule. We've got to go back to our solubility rules. Anything of group 1 is aqueous, or you could use the chloride rule, all except lead, mercury, and silver, so that includes sodium chloride. Water, on the other hand, is not aqueous. Water is a liquid. So we're going to break apart the ions. H plus, Cl minus, Na plus, OH minus, all aqueous. On the product side, Na plus, Cl minus, and then HOH, liquid, stays together. Cancel your spectator ions, and we're left with the net ionic equation. It looks like this. H plus from our strong acid, OH minus from our strong base, both aqueous, will form water. And we call this an acid-base double displacement, or If proper amounts of these are mixed, meaning no excess acid or no excess base, then we also call it a neutralization reaction. Looks a little bit different when we work these problems and we have a weak acid or a weak base. We're going to take HC2H3O2, which is acetic acid, and we're going to add that to NaOH. Now again, as far as looking at this and predicting what would happen, you're still going to go through, looks like double displacement, NaC2H3O2, sodium acetate, and HOH liquid. Here's where the difference comes in, and this gets a little bit questionable. On a net ionic, what we have to understand about acetic acid is, in theory, it is aqueous, but it's not 100% aqueous. It's actually a very, very low percent aqueous, and that opens up a whole other field of chemistry where we have to study the fact that it doesn't fully ionize. Only small percents ionize, and that gives rise to what we call acid-base equilibrium for weak acids and weak bases. In terms of a net ionic, it really doesn't matter what subscript we put here. In theory, it is technically aqueous, but my fear is you put aqueous, you're going to break that apart. So I'm just not going to put anything there or an X. I'm just going to say I'm going to leave that together. Sodium hydroxide is a strong base, so I'm going to break that apart. And here we got a sodium acetate, and the acetate rule, all acetates are aqueous and all group 1 are aqueous. So we get something that looks like this: HC2H3O2 plus Na plus OH minus. I'm breaking that one apart because it's aqueous. Arrow Na plus C2H3O2 minus plus HOH. And I'm going to cancel out the spectator ions, leaving me with acetic acid plus hydroxide ion for my strong base forms the acetate ion and HOH. Now this is also a really good place to talk about the fact that this is an acid. Specifically, it is a weak acid. This is generic representation of my base, or it's my strong base because it's hydroxide. And then on the product side, when the acid gives up the H, we get something called a conjugate base, meaning the acid leaves behind a base. Now I go into a lot more detail with regard to that in some of the videos on equilibrium, but by definition, when you take an H away, you're left with an anion that can gain an H, so that means it's a proton acceptor or an H plus acceptor, so by definition that makes this a base. And then in theory, the base gains the H, and we actually call this a conjugate acid. And the word conjugate just means it's on the product side. Again, the base gains an H to form an acid. The acid loses an H to form a base. So that's what we see when we do a net ionic, in that case where we had a weak acid and a strong base. In similar fashion, but slightly different, HCl, that's aqueous, that's a strong acid, hydrochloric acid, is added to ammonia. Now ammonia is a weak base, and it's kind of the same thing. In theory, it's aqueous, but there's nothing there that we're going to break apart on that. And on this one, when we predict the product, it gets a little bit weird. You actually would probably picture this as a synthesis reaction, meaning NH4Cl, but that is an ammonium salt plus the chloride rule. So either rule, both of those, tell me that this is going to break into the ammonium ion and the chloride ion when I do my net ionic equation. So I'm taking those apart on the product side. Again, the NH3 I'm going to leave together. And the HCl here I'm going to break apart, H plus Cl minus, because it is a strong acid. And in this one, if I cancel out these, here's what I'm left with. This is my strong acid, weak base. And then again, if this is the base gains the H to form what we call a conjugate acid, NH4. The ammonium ion has an extra H, so it by definition is an acid, conjugate because it's on the product side. And even though I've canceled out the spectator ion, this is what's left of that acid once it donates that H, so this is my conjugate base. Again, in terms of the net ionic, the chloride ion is not going to be there. It's going to be canceled out as a spectator, but it is a conjugate base by definition. So that's a little bit on acid-base double displacement reactions, but now I want to get more into what we call precipitation double displacement reactions, and this is where solubility rules become of the utmost of importance. So KNO3, potassium nitrate, and this might say a solution of potassium nitrate, a solution because it's a nitrate and it's a group 1A salt, is added to a solution of sodium chloride. Again, two rules there. Whichever rule you want to exercise, both support the fact that that is going to be aqueous. And this looks like it might be a double displacement reaction. So I'm going to go ahead and do that. NaNO3 plus KCl. And because these are solutions, that means there's water present. I have to ask myself, is there a rule that tells me about this? Group 1A, aqueous, nitrate's aqueous. So that is definitely aqueous. Group 1A, aqueous, all chlorides except lead, mercury, and silver, so either rule, that's also aqueous. So now when I do the net ionic, I get K plus NO3 minus plus Na plus Cl minus arrow Na plus NO3 minus plus K plus Cl minus. And if I cancel out my spectators, we're going to find that everything in this reaction cancels, meaning we start with ions and we end with ions, and there's no driving force for this reaction. So the answer to this question is this does not react. There's not any type of precipitant there that's going to form. There's nothing that drives this that'll make those ions react when we put them together. All right, so the next one that I want to do is a little bit different. AgNO3, and that might say a solution of silver nitrate is added to a solution of sodium chloride. And then I might say predict the products, balance the equation, give me the net ionic equation, all of those things. What type of reaction is it? Looks like double displacement, so NaNO3 plus AgCl. I already told you by way of the question, again, this would have probably words. You would have to know the nomenclature. A solution of silver nitrate is added to a solution of sodium chloride. And you would start with your nomenclature with those two things. You would predict the products. You would balance that equation. Now we get to the product side. Sodium nitrate, two rules. Both tell me it's aqueous. All chlorides except lead, mercury, and silver. So there's the driving force. That precipitates. It forms that solid. So this one will react. When I do the net ionic equation, Ag plus NO3 minus plus Na plus, I'm breaking apart the things that are aqueous. Cl minus, there's my reactant side. Product side, I'm going to break apart the first one, Na plus, NO3 minus, but I'm going to leave the AgCl together because it is a precipitant. It's a solid. Cancel the spectator ions, and I'm left with Ag plus Cl minus, arrow, AgCl solid. So there's the net ionic equation for a precipitation reaction. That shows me the silver ions in the presence of chloride ions, they will precipitate. They'll form that solid silver chloride. All right, so the next one here that I want to do is barium nitrate. Nomenclature exercise here. Barium nitrate is not just BaNO3, but it's BaNO3 It is a nitrate, so it is aqueous. So I might have said in the problem, a solution of barium nitrate is added to a solution of potassium sulfate, K2SO4. Again, if you need further understanding of nomenclature, you can go back and check out some videos, and I talk about how to write formulas for ionic compounds to get those correct. And this looks like double displacement, so we're going to get KNO3. That's a nitrate with a group 1, so that's going to be aqueous, so that won't drive this reaction. Barium with sulfate. Barium is a +2, sulfate's a -2, so we get BaSO4. All sulfates are aqueous except lead, mercury, barium, and calcium, so this one's going to be solid, so there's my driving force. I want to balance that equation, and 1 barium, 2 nitrates. I need a 2 here, which also fixes the 2 for the potassium, so I get 1, 1, 2, 1. And now I'm ready to go to the net ionic, breaking all this apart. Ba++ plus 2 NO3 minus plus 2 K plus. I'm taking apart everything I put together, plus an SO4 minus 2. If it's aqueous, take it apart. 2 K plus, coefficient 2 is the reason for the 2 there. 2 NO3 minus, and then lastly I'm going to leave the BaSO4 together because it's a solid, and I'm ready to cancel any spectator ions. 2K plus, 2K plus, 2 nitrate, and I'm left with a net ionic. Ba++ aqueous plus SO4 minus aqueous, arrow, BaSO4 solid. So again, this is a precipitation reaction.